Before we dive in, please remember that this presentation is for educational purposes only. The patterns and examples we discuss are general concepts and not specific implementation advice for your unique systems. Always consult with your architectural team before making changes to a production environment. Picture this: your company just launched a brand new, shiny e-commerce website. Sales are absolutely booming. The marketing team is popping champagne. But behind the scenes in the server room, it's a 5-alarm fire. The new website, built with the latest and greatest technology, has no idea how to talk to the 30-year-old inventory system chugging away on a server in the basement. So, when an order comes in, someone, let's call him Dave, has to manually type that order from one screen into another. All day. But it gets worse. The inventory system can't automatically talk to the shipping department's software, which was bought from a completely different company. So Dave has to print out the order, walk it down the hall, and hand it to Susan, who then types it into her system to print a shipping label. Meanwhile, a customer calls support wanting to know where their package is. The customer service team uses a sleek, cloud-based CRM, but it has no connection to the shipping software or the inventory system. They have to put the customer on hold, yell across the office to Susan, who yells back a tracking number, which they then relay to the customer. This isn't a hypothetical nightmare. This is the daily, grinding, soul-crushing reality for thousands of businesses, big and small. It's a state of digital chaos where every piece of software is a lonely island, and the only bridges are overworked people like Dave and Susan, acting as slow, expensive, error-prone human APIs. Now, you might think the problem is bad software or lazy developers, but it's not. The problem is success. The problem is growth. Companies grow by adopting the best tools for the job. You buy Salesforce for customer management, SAP for finance, a custom-built application for your warehouse, because each one is excellent at its specific task. The problem is, they were never designed to speak the same language. They were never meant to work together. So we end up with what architects call a spaghetti architecture, a tangled, brittle mess of point-to-point connections. Every time you add a new system, you have to weave another strand of spaghetti into the bowl, making the whole thing more fragile and impossible to understand. One small change over here causes a catastrophic, unforeseen failure over there. Progress grinds to a halt, innovation dies, and your company's technical debt skyrockets until you can barely keep the lights on. What if I told you there's a playbook? A set of proven, battle-tested strategies for taming this chaos? A universal language for making any software, old or new, cloud-based or on-premise, talk to any other piece of software, seamlessly and reliably. It's not magic. It's a discipline, a way of thinking, established by the brightest minds in software architecture over decades of trial and error. It's called enterprise integration patterns. And over the course of this series, we are going to pull back the curtain and demystify every single one of them. We're going to give you the exact vocabulary and mental models used by top architects at companies like Amazon, Netflix, and Google to build systems that are robust, scalable, and don't fall apart when you look at them sideways. By the end of this series, you will have a toolkit that will fundamentally change how you view software. You'll learn how to stop building fragile, one-off connections and start designing elegant, future-proof solutions. You'll understand not just the how, but the critical why behind building systems that last. Whether you're a developer, an architect, a project manager, or a CTO, this knowledge will make you immensely more valuable because you will hold the key to solving one of the most expensive and complex problems in modern business. So how do we start? We start by throwing out the single biggest assumption that creates the entire mess in the first place. We have to stop thinking of systems talking to each other like a phone call. In a phone call, you dial a number the other person has to pick up, you talk, you wait for them to respond, and the line is tied up until you both hang up. If the other person doesn't answer, the call fails. If their line is busy, the call fails. If you get disconnected, the message is lost. This is how most naive integrations are built. System A directly calls System B and waits for a response. It's fragile. It's tightly coupled. The patterns teach us a better way. Instead of a phone call, think of it like sending a letter. You write a letter, you put it in an envelope with an address, and you drop it in a mailbox. You don't know or care exactly when the mail carrier picks it up, or what route they take, or when the recipient reads it. You just trust the postal service to get it there. You post your letter, and you can immediately move on with your day. This is the core, foundational concept of modern integration, asynchronous messaging. Instead of directly calling each other, our applications communicate by sending messages. They package up a piece of information, send it off, and then get back to work. This simple shift in thinking solves a huge number of problems right off the bat. First, it decouples our systems. The e-commerce website doesn't need to know anything about the inventory system. It doesn't need to know its location, what technology it's built with, or even if it's running at that exact moment. Just needs to know how to send a letter. This means you can completely replace or upgrade the inventory system later, and the website doesn't have to change one single line of code. It's total freedom. Second, it provides incredible reliability. What if the inventory system crashes? If it were a phone call, the order would be lost forever. But with messaging, the letter just sits safely in the mailbox, waiting for the inventory system to come back online. When it does, it picks up its mail and processes all the orders that came in while it was down. No data is lost. The business keeps running. This brings us to our very first two patterns. They are the absolute bedrock of everything else we will learn: the message and the message channel. First, the message. A message isn't just a random blob of data. It has a specific structure, just like a physical letter. It has two parts: a header and a body. The body, or the payload, is the actual content. It's the letter itself. In our e-commerce example, the body of an order message would contain the customer's name, the shipping address, and a list of products they bought. It's the what. The header is the metadata. It's the envelope. It contains information about the message. Things like a unique ID for the message, a timestamp of when it was sent, a return address, and maybe information about what kind of message it is, like order created. It's the who, when, and where. This separation is critical. It allows systems to route, filter, and inspect messages without ever having to look at the actual data inside. So we have our message, but where does it go? It doesn't just float in the ether. It travels on our second pattern, the message channel. A message channel is the mailbox, or the postal service in our analogy. It's a virtual pipeline that connects our applications. A sender application writes a message to a channel, and a receiver application reads a message from that channel. Think of it like a highway. One system is the on-ramp, putting cars onto the highway. Another system is the off-ramp, taking cars off the highway. The beauty is, the system putting the cars on doesn't need to know anything about the off-ramp. Just needs to know which highway to use. You could have one on-ramp and 5 different off-ramps, with each one taking cars for a different purpose. Let's apply this back to our e-commerce disaster. With our new patterns, here's how it works. When a customer clicks buy, the website application doesn't try to call the inventory system. Instead, it creates a structured, order-created message. The body contains all the order details. The header contains a timestamp and a unique order ID. Then the website puts that message onto a message channel named, let's say, New Orders. And that's it. The website's job is done. It can immediately show the customer a thank you page and is ready for the next customer. It's fast and responsive. Meanwhile, the old inventory system has been configured to listen to the New Orders channel. It sees the new message appear, picks it up and processes it, updating the stock levels. The key insight is this: the website has absolutely zero knowledge that an inventory system even exists. It only knows about the New Orders channel. Tomorrow, if the business decides to add a new fraud detection system, you don't touch the website. You simply create the new system and have it also listen to the New Orders channel. Now, both the inventory system and the fraud system get a copy of every new order automatically without the website ever knowing or caring. You've just added a major new capability with zero impact on your existing systems. This is the power of decoupling. This is the beginning of a sane, scalable architecture. We have messages and we have channels. Seems simple, and it is. But this foundation is what everything else is built upon. But what happens when the website sends a message in the modern JSON format, but the old inventory system only understands ancient XML? What if an order message needs to be sent to the inventory system, but also to the shipping system and the analytics system? How do you make sure each one gets a copy? What if you need to take an order, but before you can process it, you first have to look up the customer's credit score from a completely different system? This is where the real power and the rest of the patterns come into play. We've laid the foundation, and now we're ready to build the skyscraper. So let's tackle that first problem head-on. An order message arrives. It's clean, it's simple, it has the product ID, the quantity, and the customer ID. But our order processing system has a rule. Any order over $500 needs a credit check. The problem is, the credit score isn't in the order message. It lives in a completely separate system, the Customer Relationship Management System, or CRM. Now, the knee-jerk reaction, the thing that gets so many developers into trouble, is to say, fine, I'll just have my order processing application make a direct call to the CRM's API to get the score. On the surface, it sounds logical, but you've just done something incredibly dangerous. You've created what we call tight coupling. You've essentially welded the plumbing of your order system directly to the plumbing of your CRM. What happens when the CRM team decides to update their API? Your order system breaks. What happens if the CRM is down for maintenance? Your order system grinds to a halt, unable to process anything. You've made your application fragile and dependent. This is like building the 10th floor of your skyscraper, and then realizing you need to run a giant, immovable steel beam through it to connect to the building next door. It's messy, it's inflexible, and it's going to cause major problems down the road. The enterprise integration patterns give us a much more elegant solution. It's called the content enricher. Think of it like this. Imagine you're a head chef in a busy restaurant. A waiter brings you an order ticket. It just says, steak medium rare. That's the original message. But you, the chef, have a special system. You need to know about any customer allergies before you start cooking. Now, the bad way to do this would be for you, the chef, to stop everything you're doing, run out into the dining room, find the customer's table, and ask them about their allergies. It's inefficient, it stops the entire kitchen, and it's not your job. The smart way is to have a maitre d', a host, who acts as our content enricher. The waiter hands the simple ticket to the maitre d'. The maitre d' sees the table number, quickly looks up the customer in the reservation system, and sees a note, peanut allergy. He then takes a red pen and writes peanut allergy in big letters at the top of the order ticket before handing it to you, the chef. You, the chef, receive a complete, enriched order. You have everything you need to do your job safely and correctly, and you never even had to know the reservation system existed. You are completely decoupled from it. That is exactly what the content enricher pattern does for our software. It's a component that sits in our messaging pipeline. It receives the original simple order message, sees the customer ID. It then takes that ID and makes a call to the external system, our CRM, to fetch the credit score. When the CRM responds with a score, say 750, the enricher doesn't just pass it along. It adds it to the original message. So the message that comes out is a new, richer version. It now contains the product ID, quantity, customer ID, and the credit score of 750. The downstream order processing system receives this complete package. It has all the information it needs in one place. It doesn't know or care that a separate CRM system even exists. It just gets a perfect, self-contained message. We've successfully gathered the data we need without creating a brittle, tightly coupled mess. We've built the next floor of our skyscraper, and it's strong and independent. Okay, fantastic. Our message is now enriched. It's carrying all the data we need, but this creates a new challenge. What do we do with this information? Based on that credit score, we need to make a decision. If the score is high, say above 700, the order can be automatically approved and sent straight to the fulfillment system to be packed and shipped. But if the score is low, below 700, we can't just reject it. Maybe it's a new customer, or there's a mistake. We need to send it to a different system, a manual review queue where a human can take a look. So how does the message know where to go? It's sitting in a queue, and it needs to be sent to one of two different destinations, the fulfillment queue or the review queue. We need a traffic cop. We need something to look at the message and direct it down the right path. This brings us to our next powerhouse pattern, the content-based router. The name says it all. It's a router, meaning it directs traffic, and it makes its decisions based on the content of the message. It literally opens up the envelope, reads the letter inside, and decides where to send it next. Let's use an analogy. Imagine a bouncer at a massive nightclub. This club has two separate rooms, the main dance floor, which is for guests 21 and over, and a teen lounge with arcade games for guests under 21. A line of people, our messages, is waiting to get in. The bouncer is our content-based router. His job is to look at each person's ID, the content of the message. He's not changing the person, he's just inspecting a piece of their data. The first person walks up. The bouncer checks their ID. 25 years old. He points them to the door on the left. Main dance floor for you. The person, the message, is routed to the 21 and over queue. The next person walks up. 19 years old. The bouncer points to the door on the right. Teen lounge for you. That person is routed to the under 21 queue. The bouncer's logic is simple. If age is greater than or equal to 21, then send to channel A, else send to channel B. This is precisely what a content-based router does in our system. It pulls the enriched order message off the queue. It inspects the credit score field. It has a set of rules we've defined. The first rule says, if credit score is greater than 700, send this message to the fulfillment_queue. The message is then placed on that specific queue, ready for the fulfillment system to pick it up. If a different message comes along with a credit score of 650, the router checks its rules again. The first rule fails. It moves to the next rule. If credit score is less than or equal to 700, send this message to the review_queue. And boom, the message is routed to a completely different destination for a different business process. Notice the power here. The application that originally sent the order has no idea this logic even exists. It just fired off a simple order and forgot about it. The routing logic isn't buried deep inside some monolithic application. It's a clear, defined, and separate component in our integration layer. If the business decides to change the rules tomorrow, actually the cutoff should be 720, not 700, we can change it in one place in the router without touching the order processing system or the fulfillment system. It's flexible. It's maintainable. You can see how these patterns start to work together like Lego bricks snapping into place. The content enricher gets the data we need to make a decision. The content-based router then uses that data to execute the decision. It's a beautiful logical flow. First, we gather intelligence. Then we act on that intelligence. We've now successfully taken an incoming message, added critical information to it from another system, and then routed it to the correct destination based on that new information. Our skyscraper is starting to take shape. We have a solid foundation. And now we have a functioning, intelligent mailroom on the first floor that enriches and sorts everything perfectly. But we've just created another problem. The message for the high credit score orders has been successfully routed to the fulfillment_queue. The fulfillment department system is ready to pick it up. But there's a catch. Our message is a modern, clean JSON object. The fulfillment system, however, is a dinosaur. It's a legacy system built in the 1990s, and it doesn't understand JSON. It can only read one thing: a comma-separated value file, a CSV. So we have our new, shiny system speaking perfect English, and the old, critical fulfillment system only understanding ancient Latin. They're on the same network, but they can't communicate. How do you bridge that gap? How do you translate the message from one format to another on the fly, without forcing either system to change? The answer is you hire a translator, a specialist who sits between the two systems, fluent in both languages. This specialist is a core concept in system integration, and it has a name: the message translator pattern. This pattern is your universal adapter. It's a dedicated component whose one and only job is to convert a message from one format into another. It doesn't judge the message. It doesn't add to it or take away from it. It just translates. The e-commerce system sends its order in modern English, a language we can call JSON. The translator component intercepts this message. It reads it, understands it, and then meticulously rewrites the entire thing into ancient Latin, or what we'll call XML. Then, it passes this newly formatted XML message to the fulfillment system. The fulfillment system receives the message in the only format it understands and happily processes the order. The e-commerce system sent the message in the only format it understands. Neither system knows the other one speaks a different language. They don't even know the translator exists. All they know is that they sent a message and the work got done. This is the beauty of loose coupling. You've solved a fundamental incompatibility without forcing a single line of code to change in your core business systems. That's a massive win. You haven't had to pause your business for a 6-month rewrite of your fulfillment platform. You just slotted in a small, independent translator component. Let's make this super concrete. Your e-commerce system might send an order that looks like this in JSON: a set of curly braces with key value pairs like customer ID, 1138, product SKU, a 77Z, and quantity, 3. It's clean, lightweight, and easy for modern web services to read. But your legacy fulfillment system expects old-school XML. It needs to see something like an opening order tag, and inside that, a customer tag containing 1138, an item tag containing A77Z, and a count tag containing 3, all closed off with their proper closing tags. The message translator is the piece of code that takes that first JSON structure as input and produces the second XML structure as output. It maps customer ID to customer, product SKU to item, and quantity to count. It's a simple, predictable, and powerful transformation. But what if the problem is more complex than just the format? What if the data itself is different? This is where we move beyond simple translation and into the realm of message transformation. Imagine your e-commerce system identifies products by a product ID, which is a number, like 54321. But your warehouse system, the one that actually has the boxes on the shelf, doesn't use product IDs. It uses an alphanumeric SKU, like BK505LG. The order message from the e-commerce site is useless to the warehouse. It says ship one of product 54321, and the warehouse robot just beeps in confusion, looking for a box with that number on it. A simple message translator can't solve this. It can change JSON to XML, but it can't magically know that 54,321 means BK505LG. It needs more information. It needs to enrich the message. This brings us to our next crucial pattern: the content enricher. The content enricher is like a detective who gets a thin case file and needs to add more details before passing it on. The initial message arrives with the product ID. The content enricher sees this, and before passing the message along, it pauses. It takes that product ID, 54321, and queries another system, maybe a product catalog database. It asks the database, "Hey, what's the SKU for product ID 54321? The database responds, "That's BK505LG. Perfect. The content enricher takes this new piece of information, the SKU, and adds it to the message. Now the message contains both the original product ID and the newly acquired SKU. Then, and only then, does it send the message on its way to the warehouse. The warehouse system gets the message, ignores the product ID it doesn't understand, finds the SKU it does understand, and the order is fulfilled. This is an incredibly powerful idea. You're using data from one system to augment a message so that another system can understand it. The original message didn't have enough information to be useful downstream. The content enricher pattern fixed that by adding the missing context, pulling it from an external source. Think about another example. A customer places an order. The order message has their customer ID, but the shipping system needs their full shipping address and their customer loyalty tier to determine the shipping cost. The order message doesn't have that. So a content enricher intercepts the message. It uses the customer ID to look up the customer's profile in a CRM system. It pulls the address and loyalty status, adds them to the order message, and then sends the enriched message to the shipping system. The shipping system now has everything it needs to calculate the cost and print a label. The content enricher is the hero when a message is information poor. But what about the opposite problem? What happens when a message is information rich? When it has too much data? This leads us to the logical counterpart of the enricher, the content filter. Imagine your big, modern customer relationship management system, your CRM, is the one sending a message. When a customer status changes to gold tier, the CRM sends out a notification. But this notification is a massive data dump. It contains the customer's entire life history, their name, address, every purchase they've ever made, every support ticket they've ever filed, their birthday, their marketing preferences, everything. The CRM sends this giant blob of data because that's just how it works. It exports the whole customer record. But the only system that cares about this notification is the email marketing system. And all it needs to know is the customer's email address and their first name. So it can send a "Congratulations on reaching gold tier, Sarah" email. Sending that entire massive customer record to the email system is wasteful and risky. It's a waste of network bandwidth and processing power. And it's a security risk. The email system has no business knowing the customer's entire purchase history. You're exposing sensitive data to a system that doesn't need it. The solution is the content filter. It's a component that sits between the CRM and the email system. It receives the giant message from the CRM. Instead of passing it along, it creates a brand new, much smaller message. It picks out only the two specific fields it needs, first name and email address, and discards everything else. Then it sends this new, lean, targeted message to the email system. The content filter acts like a bouncer at a club. The original message shows up with a huge entourage of data fields. The bouncer looks at the list and says, "Sorry, only you first name and you email address are on the list. The rest of you have to wait outside." It protects the downstream system from being overwhelmed with the relevant or sensitive information. So let's recap what we've just uncovered. We have a family of patterns all focused on manipulating the content of a message as it flows between systems. First, the message translator, which changes the format of the data, like translating from JSON to XML, without changing the data itself. Second, the content enricher, which adds new data to a message. It takes an anemic message that's missing crucial information and beefs it up by fetching data from another source, making it useful for the next system in the chain. And third, the content filter, which removes data from a message. It takes a bloated, oversized message and slims it down, protecting the next system from irrelevant information and improving security and efficiency. These three patterns, translator, enricher, and filter, are the workhorses of message transformation. They ensure that the message arriving at a system's doorstep is in a format it can read and contains exactly the information it needs. No more and no less. We've solved the problem of what the message says. We've ensured it's in the right language with the right vocabulary. But this brings up a whole new, equally important challenge. We know what to say, but we don't know where to send it. Think about our online store. An order comes in. We've translated it, we've enriched it with the right SKU. It's a perfect message. But where does it go? If the customer is in California, the order should go to the Las Vegas warehouse. If they're in New York, it should go to the Philadelphia warehouse. If the order is for a digital gift card, it shouldn't go to a warehouse at all. It should go to the email delivery system. The message itself doesn't know its own destination. How do we build a smart postal service inside our system that examines each message and routes it to the correct address based on its contents? The answer is a pattern so fundamental, so powerful, it acts as the central traffic cop for your entire system. It's called the content-based router. Let's stick with our smart postal service analogy. A regular postal worker just looks at the destination address on the envelope. Simple. But our content-based router is like a super intelligent postal clerk. This clerk doesn't just look at the address on the outside. They have permission to carefully open each and every envelope, read the letter inside, understand its content and its intent, and then decide which specific mail truck it should go on. If the letter is a birthday card for grandma, it goes on the standard delivery truck. If it's an urgent legal summons, it goes on the certified mail truck with extra tracking. If it's a tax document for the IRS, it goes on a high-security armored truck. The decision isn't based on the destination address. It's based on the content of the message itself. This is precisely what a content-based router does for our software systems. It's a component that sits on a message channel, receiving every message that comes through. It doesn't just forward them blindly. It inspects the actual data inside each message, the payload, and uses a set of rules to determine where that message should go next. Let's go back to our e-commerce platform, Acme Corporation. An order comes in. The message representing that order arrives at the content-based router. The router looks inside the message. What is it looking for? It's looking for specific pieces of information, specific fields. Let's say our order message is in a common format like JSON. It might look something like this. A field called order_type is set to physical_product. Another field, shipping_country, is USA. And a total_value is $79.99. Our router is configured with a set of rules. Rule number 1 might say, if the order_type is physical_product and shipping_country is USA, then send this message to the domestic warehouse fulfillment channel. So boom, the router, having examined the content, places the message onto the channel that leads directly to the warehouse system. The warehouse gets it, processes it, and the customer's package is on its way. The original sales system didn't need to know a thing about the warehouse. It just shouted "new order" into the void, and the router handled the rest. Now let's imagine the very next order comes in. The router picks it up and looks inside. This time the order_type field says digital_download. The router checks its rules again. Rule number 2 says, if order_type is digital_download, then send this message to the digital locker provisioning channel. Instantly, the message is routed to a completely different system, the one responsible for generating a download link and emailing it to the customer. The warehouse system is never bothered. It never even sees this message, which is exactly how it should be. It has no idea how to handle a digital download, and thanks to the router, it doesn't have to. Let's push this one step further. A third order comes in. The router inspects it. The order_type is physical_product. But this time, the shipping_country field is Canada. The router consults its rules. It skips Rule 1 because the country isn't USA. It skips Rule 2. But then it finds Rule number 3. If order_type is physical_product and shipping_country is not USA, then send this message to the International Shipping and Customs channel. And just like that, the message is sent to a specialized system that knows how to handle customs forms, international postage, and currency conversion. Do you see the power here? We have one single point of entry for all orders, but they are intelligently and automatically sorted to the correct back-end processor based on their specific details. The sending application, the sales system, is completely decoupled. Its only job is to create a valid order message and send it to one and only one place. It has zero knowledge of the complex fulfillment logic downstream. This is a monumental leap in system design. Why? Because it gives us incredible flexibility. Imagine 6 months from now, Acme Corp decides to introduce a new category: high-value orders. Any order over $1,000 needs to go through a special fraud detection and manual verification process before it even touches the warehouse. Without a router, this would be a nightmare. You'd have to go back into the code of the original sales system. You'd have to add new logic, new if statements, new connections to this new fraud system. It would be messy, risky, and you'd have to redeploy a critical piece of your infrastructure. But with our content-based router, it's trivial. We don't touch the sales system at all. We simply add a new rule to our router. The new rule would be at the very top, the highest priority. If total_value is greater than $1,000, then send this message to the fraud detection channel. That's it. We deploy the change to the router and instantly, all high-value orders are being correctly funneled to the new fraud system, while all other orders flow exactly as they did before. The rest of the system is completely unaware that anything has changed. We've just altered the entire workflow of our business by changing a single piece of routing configuration. This is agility. This is maintainability. The content-based router becomes the brain of our message-based nervous system. It centralizes the routing logic. Instead of having that logic scattered across a dozen different applications, each trying to figure out where to send its data, it's all in one place. This makes the system dramatically easier to understand, to monitor, and to modify. When you need to know why an order went to a specific place, you don't go on a wild goose chase through 5 different code bases. You go look at the router's rules. It's the single source of truth for message flow. So we've solved a huge problem. We've created a smart postal service that directs messages to the right destinations. The sales system sends a generic new order message, and the router ensures it gets to the specific system that can handle it, whether that's domestic fulfillment, international shipping, or digital delivery. Our components are beautifully decoupled. Everything is working. Or is it? We've focused so far on where the message goes, but we've made a dangerous assumption. We've assumed that the system receiving the message actually understands it. Let's go back to that international order. The router correctly sends the JSON order message to the International Shipping and Customs system. But what if that system is an old, legacy application? What if it was built years ago, before JSON was popular, and it only understands a very specific, rigid XML format? The router does its job perfectly. It delivers the letter to the right address. But when the recipient opens the envelope, the letter inside is written in a language they can't read. The JSON message arrives, and the legacy system immediately chokes on it, throws an error. Unrecognized format. The order fails. The customer is left waiting. We have a communication breakdown. We've solved the where problem, but now we're facing a what problem. What format is the data in? The different parts of our system are speaking different languages. How do we build a universal translator that can sit between these systems, converting messages from one format to another on the fly, ensuring that everyone can understand each other no matter what language they speak? This universal translator is the key. It's not a piece of science fiction. It's one of the most fundamental and powerful patterns in all of enterprise integration. It's called simply the message translator. Think of it like a professional interpreter at the United Nations. You have a diplomat from France speaking French and a diplomat from Japan speaking Japanese. They can't communicate directly. In the middle, you have an interpreter who listens to the French, processes its meaning, and then re-articulates that exact same meaning in perfect Japanese. The core information, the intent of the message, is preserved, but the format, the language, is completely transformed. The message translator pattern does exactly this for our software systems. It's a standalone component that sits on a messaging channel. Its one and only job is to consume a message in one format, and produce a new message with the same essential data, but in a completely different format. Let's make this concrete. Our online store's brand new order service is a modern masterpiece. It communicates using JSON, a clean, human-readable format perfect for web applications. When you place an order, it might send a message that looks like this. A neat little package with fields for customer ID, a list of line items with product SKU and quantity, and a shipping address object. But down in the basement, the warehouse management system is a grizzled veteran. It was built in 1998, it runs on a server that probably has a floppy disk drive, and it has absolutely no idea what JSON is. It was programmed to expect one thing and one thing only: a simple comma-separated value string, a CSV. It wants the data in a single line like customer ID, product SKU, quantity, address, line 1, city, state, zip code. Without a translator, these two systems are at a complete standstill. The order service is shouting in modern English, and the warehouse system is cupping its ear, only able to understand medieval Latin. So we build a message translator. This piece of code subscribes to the orders channel. It receives the beautiful JSON message from the order service. It then systematically pulls out the data it needs. It grabs the customer ID, iterates through the line items to get the SKU and quantity, and flattens the shipping address object. Then, it carefully stitches these pieces of data together into that one specific, comma-separated string that the old warehouse system understands, and publishes this newly formatted message onto a different channel. Let's call it warehouse orders. The warehouse system, happily listening to its channel, receives a message in the only language it knows and gets to work packing the shipment. Notice the beauty of this. The order service has zero knowledge that its messages are being sent to an ancient system. It just speaks its native JSON. The warehouse system has no idea its instructions are coming from a modern web service. It just receives the CSV format it has always known. They are completely, utterly decoupled. The translator is the unsung hero in the middle, ensuring seamless communication. If we ever upgrade that warehouse system to a new one that prefers XML, do we have to change the order service? No. We just update our little translator to output XML instead of CSV. The rest of the enterprise doesn't even notice the change. That is architectural freedom. But a good translation is often more than just changing the syntax, more than just swapping curly braces for commas. It's also about changing the structure and the meaning. This is where the real power lies. Maybe the source system sends a price as a decimal like 19.99, but the target system, an old accounting mainframe, requires an integer representing the number of cents, so 19.99. The translator handles that conversion. Maybe the source system has a single name field, but the target system requires separate first name and last name fields. The translator contains the logic to split the string. This isn't just a format change, it's a data transformation. This leads us to a more sophisticated and incredibly useful variation of this pattern: the normalizer. Imagine our company doesn't just have one online store. We're a massive retailer, and we acquire inventory data from a dozen different suppliers. Each supplier has their own system, their own format for telling us what products they have in stock. Supplier A sends us an XML file where the product ID is called product _ Supplier B uses a JSON API where it's called SKU. Supplier C, for some reason, sends us a pipe-delimited text file where it's just the first value in each line, with no label at all. This is chaos. If we let this chaos spread into our core systems, every single part of our business, our website, our inventory management, our analytics, would have to write custom code to understand all 12 of these different formats. Your main application logic would become an unholy mess of if supplier is A, look for product _ID, but if supplier is B, look for SKU. It's a maintenance nightmare waiting to happen. The normalizer pattern solves this elegantly. Instead of trying to teach everyone to speak 12 different languages, we establish one single official language for our own internal systems. We create what's called a canonical or standard data model. We decide that, within our company, a product will always be represented in one specific way, with fields like internal ID, product name, stock quantity, and unit cost. This is our universal standard. Now, for each of the 12 suppliers, we create a specialized message translator, a normalizer. The job of supplier A's normalizer is to take their XML format and transform it into our standard product format. The job of supplier B's normalizer is to take their JSON and transform it into that same standard format. And so on for all 12 suppliers. All these different messy external formats get translated at the front door, right as they enter our system. Once they pass through their respective normalizers, They are all converted into our clean, consistent, canonical format. From that point on, every other system inside our company only has to deal with one single, predictable format. Our core business logic becomes dramatically simpler. It doesn't need to know anything about the suppliers or their weird data formats. It just processes our standard product model. Think of a travel aggregator website. It pulls flight information from United, Delta, American, and Southwest. Do you think they all provide their data in the same format? Not a chance. The aggregator uses a normalizer for each airline to convert their proprietary flight data into a single canonical flight object that the website can then easily display, sort, and filter. The complexity is managed at the edge, keeping the core clean. This idea of normalization, of creating a common language, is one of the most powerful strategies for managing complexity in a large enterprise. You absorb the complexity from the outside world and present a simple, unified view to your internal systems. It's a firewall for complexity, so we've figured out how to translate messages. We can change their format, their structure, and even normalize many different formats into one common standard. We've created our universal translator, allowing disparate parts of our business to finally communicate. But what happens when the translation isn't enough? What if the information we need isn't all contained in the original message? An order comes in, and to process it for shipping, we need to know the customer's shipping preference, ground or air. But that data lives in a completely separate customer database. The original order message doesn't have it. How do we reach out, grab that extra piece of information, and add it to the message before sending it along? How do we enrich our messages on the fly? This is a classic integration puzzle, and the solution is one of the most elegant and powerful patterns in our toolkit. It's called the content enricher. Think of the content enricher as a helpful librarian or a resourceful detective. Its one and only job is to take an incomplete piece of information, use a clue from it to find more information, and then attach that new information to the original, making it complete. It doesn't change the original data. It just adds to it, making it richer. Let's walk through our e-commerce example step by step. But this time we'll put a content enricher right in the middle of our message flow. So the order service publishes its message. It's a simple, lightweight message that lands on a channel. It contains the order ID, the product ID, the quantity, and crucially, the customer ID. It knows nothing about shipping addresses, and that's a good thing. It's focused on its one job. Now, instead of the shipping system picking up this message directly, our new component, the content enricher, is listening on that channel. It grabs the message. The first thing it does is inspect the contents. It sees customer ID 456. Aha! It says, "This is the clue I need." The enricher is configured to know exactly one thing. When I see a customer ID, I need to talk to the customer database. It takes that ID 456 and makes a direct, targeted query to the customer database. It essentially asks, "Hey database, give me the shipping address for the customer with ID 456. The customer database, doing its job, looks up the record and sends back the information. Shipping address: 123 Main Street, Anytown, USA. Here comes the magic. The content enricher now has two pieces of information: the original order message and the shipping address it just fetched. It performs a simple act of digital stapling. It takes the original message and adds a new field to it, the shipping address. So the message that came in was incomplete. But the message that leaves the enricher is now a complete, self-contained package of information. It has the order ID, the product ID, the quantity, the customer ID, and the shipping address. It's been enriched. This newly enriched message is then published to a different channel. Let's call it the enriched orders channel. And who's listening to that channel? The shipping system. When the shipping system receives the message, its life is incredibly simple. It has everything it needs in one neat little package. It doesn't need to know that a customer database even exists. It doesn't need a connection to it. It doesn't need to perform its own lookups. It just gets a message that says, "Ship this product to this address." Job done. This might seem like a small, simple step, but the architectural implications are massive. This is the heart of what makes integration patterns so powerful. We've just achieved something called decoupling. It's a word you hear all the time in software, and this is a perfect example of it. The shipping system is now completely decoupled from the customer database. If tomorrow the company decides to migrate from a classic SQL database to a brand new, cloud-based CRM system to store customer data, what needs to change? Not the order service. still sends the same simple message. Not the shipping service. It still receives the same enriched message. The only piece of the puzzle that needs to be updated is the content enricher. We just reconfigure it to talk to the new CRM's API instead of the old database. The rest of the system remains untouched, stable, and blissfully unaware of the change. This makes our system incredibly flexible and resilient to change. We've isolated the dependency. This pattern also promotes simplicity. Each component can be dumber, and in software architecture, dumb is often a virtue. The order service is dumb about addresses. The shipping service is dumb about where customer data comes from. The enricher is dumb about everything except its one specific task. Look up an address using a customer ID. This is the single responsibility principle in action, and it makes our systems easier to build, easier to test, and easier to understand. Think of it like getting a document notarized. You bring your document, the original message, to a notary public. The notary, our content enricher, doesn't write the document. They just inspect it, check your ID, the external data source, and then add their official stamp and signature. They enrich the document with proof of authenticity. When you take that notarized document to the next office, they don't have to re-verify your identity. They just trust the notary's stamp, the enriched data, and process your document. Now, the content enricher isn't a magic bullet. Comes with trade-offs you have to consider. First, performance. The enrichment step adds a delay. The message has to pause its journey while the enricher makes that call to the external database and waits for a response. If that customer database is slow, your entire order processing pipeline slows down. You're introducing a potential bottleneck. Second, reliability. What happens if the customer database is temporarily down when the enricher tries to call it? The enrichment fails. What should the enricher do? Should it discard the message? Should it try again a few times? Should it send the message on without the address and let the shipping system deal with the error? You have to build in a strategy for handling these failures. The enricher is now dependent on the availability of that external data source. And finally, data consistency. What if, in the split second between the enricher fetching the address and the shipping department printing the label, the customer updates their address on the website? The message is now traveling with stale, outdated information. For most e-commerce orders, this tiny window might not matter. But for a financial transaction or a real-time stock trade, it could be catastrophic. You have to understand the consistency requirements of your system. Despite these considerations, the content enricher is a workhorse pattern. You see it everywhere. When your food delivery app gets your order, it enriches it with the restaurant's location and your delivery address before sending it to a driver. When you swipe your credit card, the initial transaction data is enriched with your account history, fraud score, and credit limit before it's approved or denied. It's a fundamental building block for creating systems where data needs to be collected from multiple sources to complete a single business process. It allows us to take small, incomplete messages and build them into rich, complete instructions, all while keeping our systems clean, separated, and adaptable. So, the content enricher is our go-to tool for adding information to a message, for making it bigger and more complete. But this raises a perfectly symmetrical question. What if we have the opposite problem? What if a message comes in with too much information? Imagine a message from a giant old-school mainframe system. It's a massive data dump, a single message containing every conceivable detail about a customer. Their entire order history, their marketing preferences, their support ticket history, 100 different fields. But the next system in the chain is a lean modern microservice. It's the email service, and all it needs to do is send a shipping confirmation. Out of those 100 fields, it only cares about 2. The customer's email address and their order number. Sending that entire bloated message across the network is incredibly wasteful. It consumes bandwidth. It forces the poor email service to parse a huge, complex object just to find the 2 tiny bits of data it actually needs. It's like mailing someone a 20-pound phone book when all they asked for was a single phone number. How do we protect our services from being flooded with useless information? How can we trim a message down, filtering out all the noise and keeping only the essential valuable data? How do we put a message on a diet? The answer is a pattern so fundamental, so intuitive, you use it every single day. It's called the message filter. Think of a gold prospector standing by a river, swishing a pan full of gravel and water. Most of what's in the pan is worthless silt and rock. But somewhere in there might be a few flecks of gold. The prospector's goal isn't to analyze every single rock. It's to get rid of the junk as quickly as possible. leaving only the valuable stuff behind. The pan itself, with its ridges and the prospector's technique, is the filter. In our systems, the message filter does the exact same thing. It's a component that sits on a message channel and acts like a bouncer at an exclusive club. It inspects every message that comes its way based on a set of rules. Does this message have the VIP data field? No, you're not on the list. Get out. Does this message contain an order total greater than $1,000? Yes. Straight to the high priority queue. It doesn't change the message. It doesn't add anything to it. It simply makes a yes or no decision. You pass or you get discarded. So, in our story, the billing system is tired of getting that massive, bloated customer profile from the marketing department. It implements a message filter. The filter's one and only rule is this: I will only accept messages that contain a valid, non-empty customer field. Now, when the marketing system sends that giant message with the customer's favorite color, their last 10 purchases, their dog's name, the filter steps in. It peeks inside the message, sees the customer field, and says, "Great, this is the one piece of gold I was looking for." But it doesn't just extract the phone number. That's a different step. Instead, it lets the entire message through because it met the criteria. The billing system still has to pick the phone number out, but at least it knows it's in there. A more aggressive filter might be configured to drop everything but the phone number, creating a brand new, leaner message. This simple pattern is a lifesaver. It protects our applications from processing irrelevant data, saving precious CPU cycles and memory. It's the first line of defense against noise, the bouncer that keeps the channel clean and focused on what truly matters. But what happens when we face the opposite problem? What if the message isn't too fat, but too skinny? What if the message arrives, but it's missing a critical piece of information that it needs to be useful? Imagine a detective arriving at a crime scene. The only clue is a partial license plate on a getaway car. N4J. By itself, this is almost useless. But the detective has a powerful tool: her database. She can take that partial plate, that anemic piece of data, and query the DMV database. Seconds later, she gets a flood of new information back. The car is a 2022 blue Ford sedan, registered to a John Smith at 123 Main Street. She took a message that was data poor and made it data rich. This is the essence of the content enricher pattern. The content enricher is a component that intercepts a message that's missing information. It takes a key piece of data from the incoming message, like a customer ID, an order number, or a product SKU, and uses it to call out to an external data source. This could be a database, another web service, or a simple lookup file. It then takes the result of that lookup and adds it, or enriches the original message with this new data. Let's go back to our company. The sales department successfully closes a deal and sends a message to the shipping department. The message is simple: ship order 9-5-2-7 to customer 4-8-1-5. The shipping system gets this message and throws its hands up. Customer 4-8-1-5? Who is that? I don't have an address, I don't have a name, I can't ship this. This is where the content enricher steps in. It sees the message with customer ID 4815. It takes that ID and makes a quick call to the central customer database. The database responds with the customer's full name, shipping address, and contact phone number. The enricher then takes this new information and stuffs it right back into the message. The message that arrives at the shipping department's doorstep is now complete. Ship order 9527 to John Doe, 123, Oak Avenue, Anytown, USA, phone 555-1234. The message went from being an unfulfillable request to a complete, actionable instruction. We didn't just add data, we added value. We made the message self-contained and useful. So now we have two powerful tools: the filter, which puts messages on a diet, and the enricher, which bulks them up with necessary nutrients. We can control the amount of information, but what about the form of that information? What happens when two systems need to talk, but they speak completely different languages? It's not about missing data or extra data. The right data is all there. It's just in the wrong format. Think about traveling internationally with your laptop. Your laptop charger needs 120-volt American-style electricity with 2 flat prongs. But you've just landed in Germany, and the wall socket is offering 230 volts through 2 round holes. If you try to jam your plug into that socket, at best nothing happens. At worst, you get a shower of sparks and a fried computer. What you need is an adapter, a translator. a small device that sits in the middle. It takes the European electricity in one side and transforms it into a shape your American plug can understand on the other. It doesn't change the electricity itself, just its format. This is precisely what the message translator pattern does. The message translator is a component that converts a message from one format to another. It's the universal adapter for your entire enterprise. It doesn't add new data like an enricher, and it doesn't discard the message like a filter. It simply reformats the existing data. Let's say our marketing system is an old, legacy application. It's been around for 20 years, and it thinks the height of technology is XML. When it sends customer data, it sends a big, clunky XML document with lots of tags and brackets. But our brand new billing system is a modern cloud-native service. It's sleek, fast, and it only speaks JSON, a much more lightweight and modern data format. When the marketing system sends its XML message, the billing system sees it as complete gibberish. It's like trying to read a book in a language you don't understand. The words are there, but they have no meaning. So, we place a message translator between them. The XML message from the marketing system flows into the translator. The translator carefully reads the XML, understands its structure, and then painstakingly rebuilds the exact same information in a different format. It maps the customer name XML tag to the customer name JSON key. It converts the order ID equals 123 structure into a neat JSON object. The message that comes out of the translator has the exact same semantic content as the one that went in, but its structure is completely different. The billing system receives this perfectly formatted JSON, understands it instantly, and processes the payment. The two systems, old and new, written in different languages by different teams in different decades, can now communicate flawlessly, and neither one has to be changed. The translator absorbed all the complexity, allowing each system to remain blissfully ignorant of the other's internal workings. These three patterns, the filter, the enricher, and the translator, form a powerful trio for manipulating the very content of our messages. They allow us to slim messages down, bulk them up, or completely change their clothes. They are the sculptors that shape our data as it flows through the enterprise. But this raises a critical question. We can now change the format of a message from XML to JSON. But what happens when the problem is more subtle? What happens when two systems both send JSON, but they use different names for the same thing? The marketing system sends a message with a field called customer_ID. The sales system sends a message about the same customer, but it calls the field account number. And the support system calls it client identifier. It's all the same piece of data, that unique number for a customer, but everyone has a different name for it. How do you build a system that can understand all these different dialects? How do you create a single, unified, canonical language for your entire business, so that a customer ID is always called the same thing no matter who is talking? How do you build a Rosetta Stone for your enterprise? The answer is a pattern so fundamental, so powerful, that it acts as the central nervous system for your entire data strategy. It's called the canonical data model. Canonical in this sense just means standard or authoritative. Instead of trying to teach every single application how to speak every other application's language, a recipe for chaos, you establish one single official language for your business. This is your Rosetta Stone. This is your universal translator. Think of it like the United Nations. You have hundreds of delegates, each speaking a different language. Now, imagine the nightmare if you had to hire a translator for every single possible pair. A Japanese to German translator, a German to Swahili translator, a Swahili to Portuguese translator. The number of translators would explode. It would be unmanageable. What do they do instead? They establish a few official, canonical languages. A delegate from Japan speaks to their translator, who converts their Japanese into English. The delegate from Germany then listens to the English translation and understands. You don't need a Japanese to German translator. You just need a Japanese to English one and a German to English one. The canonical data model is the English of your enterprise. Your CRM might call a customer a contact. Your billing system might call them a client. Your shipping system might call them a recipient. In your canonical data model, you decide once and for all they are a customer. A customer has a customer ID, a first name, a last name, and a shipping address. That's the law. Now, when the CRM wants to send information, it doesn't send its native contact object. Instead, a special component translates that contact into the official canonical customer format. That customer object is then placed on the message bus. The billing system can then pick it up and translate it into its own client format. The magic here is decoupling. The CRM no longer needs to know or care about how the billing system is structured. The billing system has no idea what the CRM's data looks like. Neither of them needs to change if a third system like a new shipping platform is added. As long as the new system can speak the canonical language, it can immediately start communicating with everyone else. You've just reduced a tangled web of n-squared connections down to a simple hub-and-spoke model. This is architectural elegance. But this raises a crucial question. What is that special component that does the translating? This brings us to our next essential pattern, the translator, or more specifically, the data mapper. The data mapper is the workhorse. It's the UN translator in the booth, tirelessly converting one language into another. It's a component that takes a message in one format, applies a set of rules, and outputs a message in a different format. It's where the rubber meets the road. A mapper might do simple one-to-one mapping. For example, the source message has a field called c_name, and the canonical model has a field called customer name. The mapper just connects the two, but it can get much more complex. It might need to combine fields like taking first_name and last_name from the source and concatenating them into a single full name field in the canonical model. It might need to perform lookups or conversions, like changing a country code from US to the full name United States. It might even have to apply business logic, like calculating a total price by multiplying quantity and unit_price from the source message. Tools like MuleSoft, Boomi, or even code libraries provide powerful graphical interfaces to build these maps, dragging and dropping lines from a source schema to a target schema. Every time a message flows from an application to the integration layer, it passes through a mapper to be converted into the canonical format. And every time it leaves the integration layer to go to a target application, it passes through another mapper to be converted into that application's native format. Okay, so we have a standard language and translators to enforce it. But what happens when a message doesn't have all the information it needs? Imagine an order comes in from your e-commerce website. The message contains the order ID, the product ID, and the customer ID. It's a perfectly valid message. But to actually process this order, the fulfillment system needs more. It needs the customer's shipping address and their credit status. That information isn't in the original message. What do? This is where the content enricher pattern comes into play. It's like a helpful researcher who sees your message is a little thin on details and goes and finds the missing information for you. The content enricher is a step in your integration flow that takes the incoming message, looks at the data it contains, in this case the customer ID, and then uses that data to call out to another system to retrieve the missing pieces. So the flow looks like this. The order message arrives. The content enricher sees the customer ID. It then makes a call to the main customer database or CRM API, saying, "Hey, for this customer ID, give me their shipping address and credit status." The database returns the needed information. The content enricher then enriches the original message by adding these new fields. Now, when the message is sent on to the fulfillment system, it's complete. It has everything that system needs to do its job, all in one neat package. The fulfillment system didn't have to make a separate call. It was handed a perfect self-contained unit of work. This pattern is incredibly common and incredibly useful for creating robust, independent services. Now let's flip that coin. What if a message has too much information? Let's stick with our order message. After being enriched, it might contain the customer's entire order history, their marketing preferences, their date of birth, their shipping address, and the details of the current order. It's a big, rich message. It's perfect for the data analytics team. But what about the billing system? The billing system only cares about three things: who to bill, what they bought, and how much it cost. Sending it the customer's date of birth and marketing preferences is not only inefficient, wasting bandwidth and processing power, it can also be a security and privacy risk. You want to follow the principle of least privilege. Systems should only have access to the data they absolutely need to function. This is the job of the content filter. If the content enricher adds data, the content filter takes it away. It's like a bouncer for your data. Before the message is sent to the billing system, it passes through a filter. This filter looks at the message and strips out everything except the required fields: customer ID, the list of items, and the total price. A new, leaner message is created and sent to billing. This keeps your system interactions clean, secure, and efficient. Each system gets a message that is tailor-made for its specific needs. Finally, let's talk about a big problem. A really big problem. Literally. What happens when the data you need to move isn't just a few fields of text but a massive file? A 100 megabyte PDF, a 500 megabyte video file, or a gigabyte of sensor data? Trying to stuff a giant file like that into a message is like trying to ship a piano through the regular mail. It's going to be slow, it's going to clog up the entire postal system, and most message queues will just flat out reject it because it's too big. The solution is an incredibly clever pattern called claim check. Think about it. When you go to a coat check at a fancy restaurant, you don't leave your table and drag the entire coat rack with you. That would be absurd. You hand over your coat and they give you a small lightweight ticket, a claim check. You can easily carry that ticket around. When you want your coat back, you present the ticket. The claim check pattern does the exact same thing with data. Before sending the message, a component takes the huge payload, the piano, the video file, and uploads it to a shared, accessible storage location like an Amazon S3 bucket or a network file server. That storage system then gives back a unique identifier for that file, like a URL. This URL is the claim check. Now you create a very small, lightweight message. Inside this message, instead of the giant file, you just put the claim check, the URL. This tiny message flies through the messaging system almost instantly. When the receiving application gets the message, it reads the claim check, and then it's the receiver's responsibility to use that URL to go directly to the storage system and download the large file. The messaging system is never burdened with the large payload. It remains fast and responsive, only ever handling small, simple messages. This pattern is absolutely essential for any architecture that deals with large binary data, and it's a brilliant way to separate the orchestration of a task from the actual heavy lifting of data transfer. So, through the canonical data model, the translator, the enricher, the filter, and the claim check, we've taken control of our data. We've transformed it, shaped it, and ensured that every message is a perfect, purpose-built package of information. But now that our messages are perfect, a new massive challenge appears. We have all these messages flowing through our system. How do they know where to go? What if a single order message needs to be sent to 3 different places? The warehouse, the billing department, and the fraud detection engine, all at the same time. How do you build the smart, dynamic GPS for your enterprise data? This is the fundamental challenge of a growing system. Routing. And the answer is a set of patterns that act as the intelligent traffic control system, the GPS, for all your enterprise data. The simplest and most foundational of these patterns is called the message router. Imagine a busy intersection in a city. In the middle stands a traffic cop. Cars come from one main road, and the cop directs each one down a different street based on some rule. A delivery truck goes left towards the industrial district. A passenger car goes straight towards downtown. A bus turns right towards the transit center. The message router is that traffic cop. It's a component that sits on a channel, consumes a message, examines it, and then republishes that exact same message to a different channel, all without changing the message itself. It's a pure logistics expert. It doesn't care what's in the boxes, only where the boxes are supposed to go. But this immediately raises the most important question. How does the traffic cop know where to send each car? How does the router decide? This is where the rail intelligence comes in, with a more specific pattern called the content-based router. The name tells you everything. It makes its routing decision based on the content of the message. It opens the envelope, reads the address, and puts it in the correct mail slot. Let's go back to our e-commerce order. The order message arrives on a central new orders channel. A content-based router is listening. The first thing it does is inspect the message content. It looks for a field, let's say order total. If the total is over, say $5,000, the router immediately sends that message to the high-value fraud check channel. Another rule looks at the shipping address field. If the country code isn't US, it routes the message to the international shipping channel, where a different system handles customs and duties. A third rule might check for a product type field. If the type is digital download, it routes the message straight to the email delivery channel, completely bypassing the physical warehouse. You see the power here? It's a series of if-then-else statements for your data flow. If the order is high value, then send it here. Else, if the order is international, then send it there. Else, send it to the standard domestic warehouse channel. This single pattern is the workhorse of enterprise integration. It allows you to create incredibly sophisticated business logic and workflows without a single line of code in your core applications. The billing system doesn't need to know about fraud checks. The warehouse doesn't need to worry about international shipping. They just listen on their dedicated channel for the work they are supposed to do. And the content-based router acts as the brilliant, tireless dispatcher, making sure they only get the messages they care about. Now, sometimes the logic is even simpler. It's not about choosing between path A, B, or C. It's just a simple yes or no. Should this message proceed? Or should it be stopped right here? For this, we have a specialized and very common pattern, the filter. Think of a filter as a bouncer at an exclusive club. The bouncer's job isn't to direct you to different rooms inside. Their job is to check your ID against the guest list. If you're on the list, you go in. If you're not, you're turned away. The message is either allowed through to the next channel, or it's discarded completely. It's a binary decision. Where would you use this? All over the place. Imagine your systems generate a lot of diagnostic or debugging messages. You might want to see these in a development environment, but you certainly don't want them cluttering up your production systems. You can install a filter that inspects each message for a priority field. If the priority is debug, the filter simply discards it. The message vanishes. No downstream system ever has to waste time processing it. Or maybe you want to filter out duplicate order submissions that sometimes happen with web forms. A filter can check an order ID against a list of recently processed IDs and discard any duplicates it finds. The filter is the ultimate gatekeeper. It reduces noise, cleans up your data streams, and ensures that only valid, relevant messages proceed through the system. So the content-based router is the dispatcher choosing one path out of many. The filter is the bouncer making a simple yes/no decision. But this brings us back to the question that started this section. What if you need to send a single message to multiple places at once? That order message needs to go to the warehouse, billing, and fraud detection. A content-based router won't work, because it chooses only one destination. For this, we need the recipient list pattern. A recipient list is like a smart mailing list. It looks at a message and, based on its content, calculates a list of all the channels that should receive it. Then it sends a copy of that same message to each and every channel on that list. It's not an either/or choice, it's a one-to-many broadcast. So our new order message arrives. The recipient list component inspects it. It sees it's a standard physical product for a domestic customer. Based on its rules, it determines a list of recipients: the warehouse fulfillment channel, the billing system channel, and the analytics engine channel. It then makes 3 identical copies of the original order message and sends one to each of those 3 channels, all happening in parallel. The beauty is that this list can be dynamic. Maybe for orders over $5,000, the rule adds a 4th recipient to the list, the high-value fraud check channel. For a customer's very first order, perhaps it adds a 5th recipient, the welcome email channel. The sending application doesn't need to know about any of this. It just fires one message into the system. The recipient list acts as the central hub, ensuring that everyone who needs to be notified is notified, without the sender having to manage that complex list of destinations. These routing patterns, the content-based router, the filter, and the recipient list, are not mutually exclusive. In fact, their true power is unleashed when you chain them together. A message might first hit a filter to weed out test data. The valid messages that pass through might then go to a content-based router that separates them into high-priority and low-priority channels. Messages on the high-priority channel could then be processed by a recipient list, which sends them to both an alerting system and the primary processing system. By combining these simple, powerful patterns, you can build a data nervous system of immense complexity and intelligence. You can orchestrate workflows that react and adapt to the data flowing through them, ensuring every piece of information gets to the exact right place at the exact right time. We have solved the logistics. We've built the ultimate, intelligent, automated postal service for our enterprise. The messages are being delivered flawlessly, but this exposes one final colossal problem. A problem that can bring the entire system to a grinding halt. We've worked so hard to make sure the right envelope gets to the right mailbox. But what happens when the person opening the envelope can't read the letter inside? What happens when our warehouse system expects to receive instructions in a perfectly formatted XML document, but our order system sends a JSON message? What if our European billing partner requires all monetary values in euros, but our system sends US dollars? The message arrives, but it's useless because it's in the wrong format, the wrong structure, the wrong language. We've mastered the routing of information, but how do we handle the translation? This is the final and perhaps most crucial piece of the puzzle. It's the difference between a message arriving and a message being understood. We solve this with the fourth and final category of patterns: transformation. Message transformation patterns are all about changing the message itself. They don't care where it's going. They care about what it is. They are the universal translators, the editors, and the researchers of our integration pipeline. The most fundamental of these is the message translator. It does exactly what it sounds like. It takes data in one format and translates it into another. It sees a price in euros and, based on a rule, converts it to US dollars. It sees a date formatted as day, month, year, and translates it to month, day, year. For a system that expects it that way, it's a simple, direct, one-to-one conversion of content. But what if the message is missing information? Imagine an order message arrives with just a customer ID and a product code. The billing system needs more. It needs the customer's full name, their shipping address, and the price of the product. The original message is incomplete. This is where we use a content enricher. This pattern acts like a detective. It receives the partial message, looks at the customer ID, and queries a customer database to fetch the name and address. It looks at the product code and queries a product catalog to get the price. Then, it enriches the original message by adding this new information and sends the complete, self-contained message on its way. Now the billing system has everything it needs in a single package, without needing to make its own database calls. It's made the downstream components' job simpler. Now let's flip that scenario. What if the message has too much information? Imagine a complete customer record is sent from your CRM system. It has their name, address, purchase history, contact preferences, and even their credit card number. But this message is headed for the marketing department's email system. They only need the customer's name and email address to send a newsletter. Sending the entire record is inefficient and, more importantly, a huge security risk. You don't want sensitive financial data floating around in systems that don't need it. The solution is the content filter. It's like a bouncer for data. It intercepts the bulky message, plucks out only the fields that are needed, the name and email, and discards the rest. It creates a new, leaner message and sends that forward. It protects data and reduces network load. Finally, we have one of the most powerful transformation patterns, the normalizer. Imagine your company takes orders from 3 different sources: your own website, Amazon, and a corporate partner's API. Each one sends you an order message, but they're all structured completely differently. Amazon's message has a field called buyer email. The partner API uses customer_contact_mail, and your website uses customer email. Your poor order processing system would need to have special code to handle each of these variations. It would be a brittle, complicated mess. The normalizer solves this. It creates a single, common, or canonical data format for an order that your entire internal system will use. The normalizer sits at the edge of your system, receives messages from all external sources, and translates each one into your standard, canonical order format. From that point on, every other component in your system, billing, shipping, inventory, only ever has to deal with one predictable structure. It decouples you from the chaos of the outside world. So we have messaging systems to transport data, endpoints to connect applications, routers to make decisions, and transformers to translate and reshape the data. Now let's put it all together. Let's follow a single online order from the moment you click buy to the moment it ships, and see how these patterns create a symphony of controlled chaos. You're on a website, you find a product you love, and you click complete purchase. In that instant, the web server doesn't try to handle everything itself. Instead, it creates a simple order-placed message. It contains your customer ID, the items you bought, and the total cost. It then uses a messaging gateway to publish this message onto a message channel. Let's call it the new orders channel. The website's job is done. It can immediately tell you, "Thank you for your order," without waiting for anything else to happen. Listening to the new orders channel is a message endpoint, the entry point to our order processing system. The first thing it does is send the message to a normalizer. Why? Because maybe this order didn't come from our website. Maybe it was fed in from a partner system with a different format. The normalizer ensures that no matter the source, it's now in our standard, internal order format. Next, the normalized message hits a content-based router. This router is the traffic cop. It inspects the message content. Is the order total over $5,000? If yes, it routes a copy of the message to a fraud detection channel for special review. Is the shipping address international? If yes, it routes the message to the international processing channel. For all other standard, domestic orders, it sends the message to the standard fulfillment channel. Let's follow the standard path. The message arrives on the standard fulfillment channel, but it only contains your customer ID. The warehouse needs your actual shipping address. So the message is immediately consumed by a content enricher. This component takes the customer ID, looks you up in the customer database, and adds your full name and shipping address to the message. The message is now enriched and ready for the next step. The enriched message now needs to inform several departments at once. The inventory needs to be updated, the warehouse needs to pack the box, and the finance department needs to record the sale. This is a perfect job for a recipient list router. It takes the single, enriched order message and sends a copy to 3 different channels simultaneously: the inventory, shipping, and billing channels. We're using a publish-subscribe channel model here. Now let's look at the shipping channel. The warehouse management system is listening, but does it need to know your credit card information or your purchase history? Absolutely not. So before the message gets to the warehouse system's endpoint, it passes through a content filter. This filter strips out all the sensitive financial data and personal information, leaving only what's necessary: the customer name, the shipping address, and a list of items to pack. The warehouse gets a lean, secure, purpose-built message. Each of those 3 systems, inventory, shipping, and billing, has its own endpoint, consumes its tailored message, and does its job. The inventory system decrements the stock count. The shipping system prints a label and alerts a worker. The billing system records the transaction. And once the warehouse ships the package, its system might publish a brand new message, an order shipped event, back into the messaging system, which could then be picked up by a notification service to send you that your order is on its way. Email. What have we accomplished? We've built a system that is incredibly resilient and flexible. This is the entire point. The magic word is decoupling. The website doesn't know or care how the warehouse works. The billing system could be written in a completely different programming language than the inventory system. They don't care. They only agree on the format of the messages they pass through the central messaging system. You can now upgrade or even completely replace the entire shipping system. And as long as the new system knows how to read an order message from the shipping channel, nothing else in the entire company breaks. The website doesn't go down. Billing continues uninterrupted. Want to add a new sales channel like a mobile app? You don't have to change your existing systems. You just teach the mobile app how to send a properly formatted, order-placed message to the new orders channel, and everything else just works. Enterprise integration patterns are not just abstract theories. They are the blueprints for building modern, scalable, and maintainable software. They are the language we use to describe the flow of data through the digital veins of a company. By breaking down complex problems into these small, reusable patterns, channels, endpoints, routers, and transformers, we move from building brittle, monolithic giants to composing flexible, resilient ecosystems. You've just learned the fundamental vocabulary for orchestrating the digital conversations that power our world.